Welcome to Lecture 9. We're about halfway through the course of Statistical Rethinking 2022, so let's spend a minute looking back at where we've been before we move forward. In the first lecture, I introduced the three overarching themes of the course, that is golems, which are the statistical engines that process scientific information, owls, a metaphor used to emphasize the importance of understanding an ordered and logical and socially justifiable workflow for how we derive inferences from data, and DAGs. DAGs are a launching point for logically connecting the scientific knowledge, the vast scientific knowledge that all researchers have, to the topics they study and the statistical tools they use to derive information from data. In the second lecture, I focused on the basic logic of Bayesian inference, which is just that we count stuff. Bayesian inference is just counting. It's a way of counting all the ways that some hypothetical process could have produced the observations. In the third lecture, I showed you how to expand that basic logic into more complicated models, familiar or perhaps unfamiliar linear regressions done in the Bayesian way. In the fourth lecture, we took those same tools, just linear regression, and built it up into much more complicated shapes. But at its core, this is still just linear regression, able to model categories and fancy curves and many kinds of phenomena. In the fifth lecture, I tried to connect those statistical tools to causal understandings, the ways that we avoid being confused and confounded and biased in our inferences, to connect our statistical tools to our scientific models in justifiable ways. In the sixth lecture, I took those fundamental tools of causal inference and built them up into much more complicated models, and showed you how to use basic criteria to derive statistical models that are specifically designed to answer specific scientific questions. In the seventh lecture, I looked at another issue just as important as causal inference and always shadowing it, which is ways to make approximations. In every scientific project, there are parts of the model which we must approximate, and so we need to understand how scientific models tend to overfit the sample and ways to control that overfitting tendency. In the eighth lecture, I introduced a bit of infrastructure. Scientific computing is just as important in this business as the concepts we use to do inference, and advances in the last 20 and 30 years in scientific computing have been substantial and make possible much more successful scientific inference than used to be true. So tools like Hamiltonian Monte Carlo, pictured here, will propel us into the second half of the course and give us a lot more expressive power to take our scientific models and express them as statistical models. In all of this, I've tried to maintain this understanding of flow. That is, it's really not possible for most people to understand everything on the first pass. This material is complicated, and all of the complexity happens simultaneously. So what's important is not that you understand everything, but that you keep moving forward. And the second half of the course will have the same strategy. There will be lots of pieces, but they will be layered in one at a time, building on the previous tools. And the good news is, for the most part, most of the conceptual work is done, and all of the pieces are in place. And the second half of the course takes the pieces of the first half of the course and applies them to new scenarios and shows you how they can be used to model different scientific contexts. So let's get started. The lecture today is going to focus on the modeling of events, which are things that we count. And when we count events, we end up with variables that are not continuous and so are inappropriate for analysis by linear regression. So what do we do instead? The motivating example for this lecture is going to be university admissions data. admissions data specifically for the University of California, Berkeley, from the 1970s. UC Berkeley has always been a very activist campus, very focused on access to higher education and equal access to higher education. And so the data set we're looking at comes from a particular historical moment in the early 1970s where the leadership at UC Berkeley was concerned that there may be discrimination against women in graduate school admissions. There's this widespread rumor that they were sued, and that's the backstory of this data set, but that isn't true to the best information I can find. It seems that maybe they were worried about getting sued, but the investigation was initiated internally because they were concerned there might be discrimination against women applicants. The data set in its entirety is shown on the right-hand part of this slide, and it's available in R and probably every other scripting language as well, because there was a prominent publication in the 1970s that came from it. If you want to chase that citation and follow some of the historical context, you can see the help as $UCB admissions inside R for more information. This data is 4,500 or so graduate school applications across 6 different departments for the 1973 application round at UC Berkeley. And they've stratified the data here by department and the gender of the applicant, the self-reported gender of the applicant. The question we're going to be focused on is there evidence of gender discrimination? Let's follow the workflow. Draw the owl, as it were. First, we're going to talk about estimands. We've already said what the estimand is in a vague way. What I'm going to show you next is that we're going to have to build up a scientific model to have a really specific scientific estimand. Then we'll turn to the statistical versions of the model and finally to the analysis. And that'll take us through the whole lecture. So let's talk about estimands and the scientific model simultaneously here. And I think you'll see that we kind of have to do that in this case because it's seemingly a simple estimand. Is there discrimination? But discrimination is not a unified thing in this system. So the basic question would seem to say that we simply want to know if gender influences the chances of someone's admission. And we do want to know that. However, this data set has another very important variable and another path through which gender might influence admission, and that is the department that a person applies to. Different departments have different base rates of admission. Some are easier to get into than others. Some are vastly oversubscribed, that is, that they get way more applicants than they can possibly accept. Others are desperate for applicants and will take nearly all of them except the unqualified. And so we have at least 2 important causal pathways through which gender might influence admission to UC Berkeley in 1973. This structure, this particular causal structure, is something you've seen before in this course. It comes up all the time. It's a basic mediation structure where there's a direct causal path here from G to A, and also an indirect pipe from G to D to A. And the total causal effect passes through both of these paths, but sometimes we want to estimate one or the other. This basic structure is extremely common in lots of systems that have to do with discrimination, and the scholarly literature on discrimination often has to deal with this kind of causal structure. You can think about this in the abstract as encounters and discrimination. So we have some exposure, if you will, a status variable X, and that's the status that might be a target of discrimination in the population. And that may directly influence the event through direct discrimination, but it may also indirectly influence the event through some encounter. And that could be entering a particular context, applying to graduate school, or other things. Let me show you just a couple examples to prime your imagination about this. And And I'm going to do this because maybe you're not interested in graduate school applications, but I want to convince you that this is a very general structure. And if we study graduate school applications in the 1973 applicant pool of UC Berkeley, we can learn some very general and useful things about systems that have this analogous structure. So grant applications, whether they're academic grants or government grants, or even private industry grants, can also have the same kind of causal structure to them. Again, there's some exposure X. This could be any kind of status, gender, nationality, whether your first language is English. This is a big thing in European debates about grants. And then F is some field of study, some specific field of study. Engineering, psychology, and so on. And then Y is the success. And this has the same structure as graduate school applications. Of course, all the details are different, but the causal structure is very similar. There is also wage discrimination. This is a huge literature. And again, there's some status we may be interested in. It could be ethnicity, cultural background, or gender, or any number of other things. And those statuses influence the occupations people end up in, and they may also and those occupations influence wage, but there also may be direct discriminatory effects on wages for people in the same occupation. And again, we've got this classic mediator triangle. Policing, I'll mention this example again at the end of the lecture, near the end of the lecture, has this same basic structure in many parts of the world. The police, unfortunately, sometimes assault citizens, and the assaults are, there's a debate about whether the assaults are warranted. And there's a huge debate about whether the assaults, warranted or not, are biased against particular ethnicities. And so again, we have some exposure, X, the ethnicity in this case. There's a direct path where the ethnicity may lead the police to be more likely to assault the person. And there's an indirect path whereby the police may simply be more likely to stop people of particular ethnicities, and they tend to assault whoever they stop. It's not a happy story, I know. Again, I'll mention this example again at the end because it does have a different feature to the data sets that arise from it, and that'll be important for us to fully pull out some of the causal implications. Let's come back to the UC Berkeley case and carry forward with modeling. So which of the paths in this DAG are discrimination? And I would argue that they all are, or both of them are. They're different kinds of discrimination, or they could be different kinds of discrimination, depending upon the assumptions you make. And what I'm going to try to do, or perhaps you could say it this way, this lecture is a prolonged argument that yet again, the causes are not in the data, and you have to put a lot of assumptions into these models in order to make inferences about things like discrimination. And that's not bad, and that doesn't mean you can't infer that there's discrimination or not, hopefully not. It just means we have to do the conceptual work, and the data themselves contain no evidence at all. So, and that applies to this case of thinking about what it means when you find some causal effect along one path or the other. The way we might, for the context of this lecture, talk about the direct path from G to A is that this is direct discrimination. And that could mean it's status-based or taste-based. And people who are familiar with the discrimination literature know the difference. I just want to very quickly explain so that you understand some of the vagueness about these causal effects and why you have to put more interpretation into them. Status-based discrimination would mean that the people reading the applications don't directly discriminate against the category, in this case, against one gender or the other. Taste-based discrimination is different. It's like it's an accident that one gender or the other is discriminated against because the people reading the applications infer that the members of one particular gender are statistically more likely to have tastes that are inappropriate to the program. And so it's gender discrimination, and it's a direct effect in this case, but in some sense there's a mediator because there's this inference going on about tastes and the statistical distribution of tastes in the population. There's big literature on both of these things, and they're both important, it seems. The other kind of path is the overhead path through the mediator. if this is the only thing that's in play, if there's no direct causal effect of gender on admission, that doesn't mean there's no discrimination effectively, even though there may not be any direct status-based or taste-based discrimination, because there will be what many people call structural discrimination. That is, if certain, there could be discrimination that leads one gender or the other not to apply to particular departments. And or it could just be tastes that leads to it. But then if some departments have better resources than others, you can end up with unequal access to higher education, even though no one means that as the result. And that's a kind of structural discrimination. Okay, let's talk about making this into those estimands. Our goal is going to be both of those passed because they're both theoretically important, as is the total causal effect. So let's think about how to take those DAGs now and make them into something that's a more fleshed out scientific model with actual functions to generate variables from other variables. So here on the slide, I've written a bare bones, simple as I could make it, generative model of that DAG. We're trying to understand how choice of department can create structural discrimination. And we're not doing any statistics yet, and we won't for a little bit. Instead, I ask you to put statistics aside and just think about science for a second and thinking about what could be going on in systems with this kind of structure. We're not yet even thinking about UC Berkeley, very abstract, generative thinking about these systems. And I want you to consider the possibility that departments vary in their baseline admission rates and what that does to the data we might observe from these systems. And so that's what I've programmed on this slide. Let me walk you through this code one line at a time to make this both more transparent as an example, but also because I really want those of you taking this course to get comfortable with writing these simulations. Every scientific project, you should be able to write a generative simulation of your theory. Otherwise, you probably don't understand your theory. So the very first line, n is 1,000, just sets the sample size. I don't need to explain that anymore. The next line, this G line that I've highlighted here, this simulates the genders of the applicants. And we just have an even distribution. The genders here are indices, the numbers 1 and 2. And we're taking sampling 1,000 of them with replacement. So we get, with some stochastic chance, we get close to an even distribution of genders 1 and 2 in this imaginary sample. The next, we can generate D. We have to do D after G because D is a function of G. And so now we take a Bernoulli sample, that's a coin flip, 1,000 coin flips, in which G determines the chances that an individual applies to one or the other departments. And to keep this simple, I've only made it so there's 2 departments. Think of them as sciences and the humanities or something like that. And all I've assumed is that individuals of gender 1, you can see in the code, if else G equals 1, tend to apply to one of the departments and rather than the other. Gender 1 tends to apply to Department 1, and Gender 2 tends to apply to Department 2. And then we can set up acceptance. Now we can simulate acceptances, and we have to do this last because acceptance to the department of choice is a function both of gender and department, or rather it can be. And the way I've set this up is I've made the acceptance rates into a matrix in which the rows are departments and the columns are genders. And in this particular example, I've made it so that there's no discrimination. Genders 1 and 2 have exactly the same admissions chances on average in both departments. But Department 1 has a much lower baseline acceptance rate. It's only 10%. And Department 2 has a 30% baseline acceptance rate. And then the last line, of course, just does the coin flips using the matrix. So what happens when you simulate a data set from this? I'm just showing you one example on the right-hand part of the slide. You should run it a number of times if you like and see what kind of variation you get for this particular sample size of 1,000. But I want you to see, using the cross tabulations on the right-hand part of the slide, is that in fact, yes, Gender 1 does end up applying to Department 1 much more than Department 2, and the opposite for Gender 2 tends to apply to Department 2. And then when we do the crosstab of gender and admission, we find the consequence of that, because of that bias in who applies to which department, that gender 1 is accepted over the whole sample. Applications from individuals of gender 1 are accepted quite a bit less than applications from individuals of gender 2. So it ends up being 19% versus 27% in this particular example. Again, you should play around with the code and see that there is variation in what you get. This example is just to show that you can get a total causal effect of gender that arises purely from the structural avenue, and that's what I've shown here. This is the mediating path. Let's modify the simulation so there is also direct discrimination against gender 1 in this case. So I've modified the accept rate matrix, so now column 1, which is for gender 1, has smaller numbers in it than the corresponding values in column 2 for gender 2. And we can run it again. And now you see you get the same pattern, actually. The same patterns in who applies to which department, and the same pattern in difference in acceptance rates. The numbers are smaller now. That's not the important thing. It's that you get the same pattern in overall acceptance rates. The appearance of the total causal effect looks the same if only one path is operating or both are. And that means we need to be a little more savvy about statistics in order to figure out what's going on here. We need to use, you guessed it, the backdoor criterion and analyze the paths separately. So before we get to the statistical part of the lecture, I just want to say about this generative model is it's leaving out a lot. I hope it works for the lesson, and that's my main objective here. But if you really wanted to study this issue, there's a lot more you could do. Admission rate really, in almost all cases, depends upon the size of the applicant pool and the resources available to the particular department. And so the distribution of qualifications of the applicants matters a lot. There's a kind of ranking process that goes on. The applications don't succeed or fail on their own, independent of who else applies, and that adds a lot of complexity to these problems. So in principle, what you'd want to do is simulate sampling of the applicant pool, and then who's accepted would be some sorting application where the applications are ranked with some error. Because of course it's anybody who's ever read applications, it's often quite hard to tell who's the best for any particular open position. We take bets. And the upshot of all this is that the acceptance rates are actually conditional on the structure of the applicant pool. So in the analysis to come, you really have to think about this as we're conditioning on the structure of the applicant pool, and we can't think about any causal interventions on the applicant pool because we haven't modeled it. We haven't modeled how it arises. We're just taking it for granted. And that's okay. You can still think through these problems and get a lot done. But I didn't want you to think that this was in any sense a complete generative model. Okay, let's talk about statistics. The point of this lecture, in the broadest sense, is to introduce you to generalized linear models. So up to this point in the course, for the last 3 weeks, we've been focusing on what are called linear models, and these are like linear regressions. In linear models, the expected value of the outcome variable is modeled as some additive or linear, in this context they mean the same thing, a combination of parameters. And so I show you the familiar linear regression that haunts your dreams on the right of the slide here, and the mean mu is a strictly additive combination of the parameters. None of the parameters are multiplying one another or exponentiating one another or anything fancy like that. You just have a bunch of additive terms, and in each one there's only one parameter. Generalized linear models, or I should say linear models are just a special and especially simple member of a family of models called generalized linear models. And in generalized linear models, the expected value of the outcome is just some function of an additive combination of parameters. And I'll say some more about what this means, some function. But the way it's always written, I'll show you on the right. Now we have something like y sub I. The outcome is a Bernoulli distributed variable, meaning 0, 1 coin flip. And for coin flips, the only parameter that determines their expected value is the probability that it takes the value 1 or takes the value 0. So p sub I here is the probability that y sub I takes the value 1. And to connect this to a linear model, you have to use some function because the linear model can take any real value. It's continuous down to negative infinity and up to positive infinity. But we need to constrain p sub I to the probability interval between 0 and 1. And that's what our sum function is going to do for us. So I appreciate that this is a bit frustrating, like what is going on here, and the notation is not transparent. So let me go through what I just said now with a little bit of ornamentation and give you another chance to catch up with it. So y sub I is a 0-1 outcome in this example, and p sub I is the probability of the event. This linear model here, which looks like every other linear model you've worked with, it's just a regression linear model. It can take any real value, from 0 up to positive infinity and from 0 down to negative infinity. It's just an additive combination of terms. And so what this function f does is it maps the probability scale to the linear model scale. And the good news is you don't have to make up these functions. There's kind of a standard set, and they work quite well in most applied contexts. But they have a logic, and I want to spend a little bit of time explaining that logic to you, so that they don't seem like magic. So these functions, like f, are called link functions. It's because their job is to link the parameters of a distribution to the linear model. In some models, you'll have more than one link function because there may be more than one parameter that describes the shape of the outcome distribution, and then we can put models on all of them, actually. There may be examples later in the course of that. If you have a link function, you also need what's called its inverse. So the function to the power of -1 is the inverse function. And the purpose of the inverse function is to undo what the link function does. And so when we write the model, the statistical model, we typically write it like I have on the top right of this slide with f of p sub I equals the linear model. But when you do the calculations in the computer, what's actually happening is you're saying p sub I equals the inverse function. And then the input into the inverse function is the linear model. So the notational way of writing it makes it easier to read. But when we do calculations, we have to do it like the bottom. And so you use the inverse function quite a lot. Just an example, abstract mathematical example, to help you understand what an inverse function is. So if you had some function of a, like squaring it, so say f is just a function that squares its input. So f of a is a squared. Let's say that a squared equals b. That's the output of the f function. The inverse function, you put the output of the ordinary function into it, and then you get the original input back. It undoes the transformation. So the inverse function of f inverse of b must be the square root of b, and that gives you a back. So that's the sense in which it's an inverse function. We don't do square and square root for probability models. Instead, we need something that transforms the real number line to the 0-1 interval, and there are multiple options, but by far the most common across fields is this thing called the Logit link, which is a weird word. Don't worry about it. I'll explain what this is. So these are used all the time in the sorts of generalized linear models we're focusing on today, these Bernoulli binomial models, which are models of count outcomes with maximum values, right? There's a fixed number of applications, and we want to model, count the number of acceptance events among them. And in these models, we use a Logit link to take the linear model parameters, which are on the real number line, and convert them to the probability space so they can predict the expected value of the outcome variable. So what the Logit function is simply log odds, and that's what I'm showing you on this slide. The odds of an event are the probability it happens, which is here p sub I, over the probability it doesn't happen, which is here 1 minus p sub I. The probability something else happens. That's the odds of an event. This is like in gambling. There are the odds that a particular card comes up in poker. And then we just take the log of it. And so this term is called log odds. So the Logit function is just the log odds. It takes the probability as an input, and what it gives you back are the log odds. And you're asking, why would you ever take the logarithm of the odds of a probability? And the answer is because it's the right transform for correctly transforming the real number line to the probability interval 0, 1 without causing any kind of asymmetric distortions and such. And actually, it arises spontaneously in the derivation of the binomial distribution. And in the book, there's an overthinking box where I derive the binomial distribution using maximum entropy, and I show you how that happens, how it arises spontaneously. This is not necessarily the reason that you need to appeal to when you use it. It works really well, and that's why we use it. The inverse function, the inverse logit there, you can call it inverse logit. You'll also see it sometimes called the logistic function because in other fields they already use this function for other things, and it happens to be called logistic. Just to demystify this, I'm going to quickly show you that the inverse logit is derived just with a tiny bit of algebra. There's nothing mysterious about it. You define the logit as the log odds, and let's let q sub I mean the log odds of p sub I. It's just the output of the logit of p sub I, as on the first line of this slide. So then what's the inverse function of q sub I? Remember, the purpose of the inverse link is that we put the result of the link function into it, and we should get the original input back. We should get p sub I back. Well, we can just use algebra. What we need is some expression represented here by the question mark, and it should be equal to p sub I. So we can just set the log odds equal to q sub I and solve for p sub I. And because that's what we want. We want something that equals p sub I and is a function of q sub I. And so if you take the equality in the lower left of this slide and simply solve it for p sub I, you get the solution on the bottom right. And this is the inverse logit function. Happens to also be the logistic function. Okay. What this function does is it makes S-curves. If the horizontal, as on the right of this slide, is a continuous log odds, the logit space, and the units on the horizontal axis there are units of log odds. Then on the vertical we have probability. Then it makes S-curves, symmetrical S-curves, or logistic curves. Some of you may know. You get good very quickly at reading log odds values, the zeros, twos, fours, minus twos, minus fours. Very quickly you learn to map them on the probabilities. So logit of 0 on the bottom axis is equal to a probability of a half, right in the middle. And then values above 0, positive values, are increasing probability. And by the time you get up to a log odds of 5 or 6, it means the probability is essentially 1. It's not exactly 1, but the event will basically always happen. And as you get increasingly negative, the event becomes increasingly unlikely. So by the time you reach minus 5 or minus 6, the event probability is essentially 0. It's never exactly 0, but gets very close to it. So the log odds span, you just have to worry about this interval between, say, minus 5 and positive 5. And that's the whole range of sensible values for the linear model component of one of these Bernoulli or binomial logit models. Let me show you the animation of this model now. Here we're just sampling the priors. I haven't put any data into this, but this is the model at the top. This is a Bernoulli model. There's an outcome. It can be 0 or 1, and that's the vertical axis on the right part. And then there's some x value, and we have this alpha plus beta x kind of linear model that you've seen many times before, and we put a logit link on it so that it maps onto a probability. And you'll see that in the prior space, I've just put a normal 0, 1 priors on both the intercept and the slope. And then we draw from these, and you've seen these sorts of animations in previous lectures. You'll see that there are lots of S-curves that are possible. They can go up, they can go down, they can be flat, they can be very steep, they can be pressed against the bottom and flat, pressed against the top and flat, and so on. And these are essentially bent regression lines. As they tilt and get up towards 1 or down near 0, they have to bend and flatten because they can't get outside of the probability space. And that's what the logit link is doing for us. Now let's introduce some data, and I want you to see what Bayesian updating does. You won't be too surprised. It does what it's always done. It learns the S-curves that are compatible with the data. That is, which S-curves have the greatest numbers of ways to produce the data we've observed, so that I'm putting in sampled points, and they always appear on 0 on the vertical axis or on 1, because those are the only observations that are possible, 0 and 1. But the function needs to predict continuous probability across values of x. That's why we see with generalized linear models, this is always true, is that the parameters we're trying to infer are not on the same scale as the data. I'll say that again. The parameters we're trying to infer are not on the same scale as the data. The data are 0, 1 events, they're counts, but we're trying to infer a probability, and a probability is a unitless number in the 0, 1 interval. And you'll see after 20 data points here, we've learned some upward sloping S-curves. Okay, how do you set priors in this place? Well, you know what I'm going to say. You do simulations to figure it out, so that's what we're going to do. But you really have to recognize that because the log-odd space, the Logit space, is constrained so much between this minus 5, minus 4, plus 5, plus 4 range, priors need to be typically pretty narrow. And then they can still fit all kinds of S-curves. Any super wide priors are going to do weird things, actually. So let me show you an example. So let's start with the world's simplest binomial GLM or Logit model, or sometimes called a logistic regression. The Logit of p sub I just equals an intercept alpha. What kind of prior distribution should we put on alpha? 3 examples on the right of this slide. These are just the prior distributions for now. The first one is a normal 0, 10 prior. That's a normal distribution with a variance of 100. And then the second one in the middle, normal 0, 1.5, and then finally normal 0, 1. What does each of these do when we transform it to the probability scale? All right, that's the implication of the prior that you should pay attention to. So let's look. We can just simulate from those normal distributions and then push the sampled values through the Logit transform. That is, we use the logistic function on them. We get probabilities out, and then we can plot the density of those probabilities. So at the top row, I want you to see, for a very wide prior in this cramped Logit or log-odd space, you're effectively assuming that the event is either destined to happen or not. That is, almost all the probability mass is outside of the minus 5 plus 5 interval. And so it's like saying that before you've seen the data, you expect that either this thing happens all the time or never. And that's why you see this bizarre prior probability distribution in the upper right, that it's an outcome of the normal 0, 10. Right, so the horizontal axis for the red curves is the probability scale. It can't go below 0, can't go above 1. In the middle, we've got something that's a little more sensible. Normal 0, 1.5 gives you a roughly uniform distribution of probabilities between 0 and 0 or 1. So you see how counterintuitive this is and why doing prior predictive simulations continues to be useful. And then finally, normal 0, 1. This is not uniform. Instead, this prior is a bit skeptical of extreme probabilities. Not very, though. Extreme. If the data mandates an extreme probability, you could definitely learn it. Okay. What if we put slopes in too? And similar kind of idea. Here's a prior predictive simulation where we have alpha and beta, and I set them both at normal 0, 10. You see that in the first 2 lines in the code box. I've done these sorts of simulations in previous lectures. The only thing that's different now is that we're doing the inverse Logit transform. It's there in the line where I compute p, the probabilities. I apply each of the x values to the inverse Logit of the linear model, inverse Logit a plus b times x. And then I get these red S-curves. And you'll see that these priors correspond to a prior information that the relationships are very strong. That is, that the S-curves are very steep, either up or down. If you make them more modest, like alpha normal 0, 1.5 and beta normal 0, 0.5, you get much more modest prior relationships between the x value and the probability. They can be positive and they can be negative, and they can still be strong, but they're not all, most of the probability mass is not under strong relationships. Okay, now we need a statistical model. We've got the basic building blocks in place, but we still need to plug in our specific example. Here's the generative model code again, just to remind you what it was, and the DAG to refresh your memory. Let's take each estimand in turn and think about the statistical model that corresponds to it. So the first estimand in this problem is the total causal effect of G on A. And you know, because you're wizards at the backdoor criterion by now, that this means that we only stratify by gender in the model. We ignore department, because if we were to stratify by department, we would block that mediating path. But we're trying to measure the total causal effect of G through both paths. So the model only needs to stratify by gender. So this is the model we want. Thinking at the top line and looking first at the left, the A sub I is distributed as a Bernoulli variable that is a function of the probability P sub I. That's where P sub I is the probability of admission, of successful application. And then we have the logit of that in the next line below it. On the right in red, I've put, in some sense, the more computational meaning of these math stat statements. What that first line with the Bernoulli in it is doing is saying that the probability that A sub I takes the value 1 is equal to P sub I. That's really all it means. And in code, that's the implication when the computer takes over. And then the second line, logit of P sub I equals alpha of G sub I, and alpha is going to be a vector of parameters. We've done this before when we analyze categories, and there'll be two parameters inside of it, one for each of the genders in this sample. And what this line corresponds to is the statement that P sub I is equal to the inverse logit of alpha of G sub I, and you'll see that in red on the right. Next estimand, we'll introduce both of these, and then we'll look at the code for both of them together as well. The second estimand is the direct effect of G. This model will also simultaneously give us, assuming the DAG is correct, the direct effect of D, the direct effect of department. And I'm going to do this as a full interaction model. So we're going to simultaneously stratify by both gender and department. So again, there's the Bernoulli line, and then all that changes is that alpha is now a matrix where the rows are genders and the columns are departments. Yeah, if there are only two departments, and there are in the synthetic example. In the real data set there are 6, but this model will accommodate however many departments or genders you want to put into it. And so we're going to estimate for each interaction of gender and department what the admissions rate is like. So here are the two models again. Now with priors, I've opted for normal 0-1 priors for the reasons that you saw a couple slides back. This will create priors that are slightly skeptical of really extremely high or low admissions rates, but only very slightly skeptical. What they don't do is put most of the probability mass on 0 or on 1, and that's a good thing. Here's the code to run these. I'm going to start using Markov chain Monte Carlo in the lectures going forward, but if you want to continue using quadratic approximation for these problems, that's fine actually. I think they'll work just fine in those systems. The one qualification about that is that this matrix notation that I'm using here in Ulam does not work in QAP. So this is a subtle way for me to urge you to get your compiler installed and start using Markov chain Monte Carlo. It'll be good for you. And besides, you'll definitely need it in probably next week. Actually, it'll be essential. So on the left, we've got the total effect model, and the formula is a typical sort of probabilistic programming translation of the math stats model. We have our vector alpha indexed by G, by genders. And on the right, the only bit of new code here is that I explicitly declare alpha as a matrix with dimensions G and D, which means what Ulam does is it looks at how many unique values there are in G and how many in D, and it makes a matrix of the appropriate size, and it names it alpha, and it gives each element of it the same normal 0-1 prior. Run these models, they run quite fast. and there's not that much data here actually in the synthetic data. So here I'm just running it on the synthetic sample that we already looked at before. We're not looking at the real data yet. That comes soon. And for the Précis output, since alpha is a vector, remember you have to tell it depth equals 2 so that it shows vectors. And you'll see that the total effect is that gender 1 has lower average admissions rates than gender 2 does. These alpha is on the log odd scale, so negative numbers mean less than 50%. And the more negative, the closer to 0 it gets. Now, and this is what the simulation assumed, recall. We did have an overall, the total causal effect of being gender 1 in the synthetic sample was to have lower overall chances of admission. And then again, for model 2, now we do depth equals 3, which means show matrix variables as well. And we get the 4 elements back. Since these models are just giving us back the generating parameters, but on the log odd scale. And that's something you should check and play around with, change the simulation values, rerun these models, and look at how they respond. You can convert all of these alphas from log odds to probabilities using the inverse Logit function, and we're going to do that. And if you do that, for example, here, just converting the posterior means of each of them, you see that they're on the probability scale again, and from a 6% chance, 21% chance, 8% chance, 20% chance. Now, of course, if you've been watching the lectures this far, that what we really want are contrasts. We want to know the differences, not the distribution of each of the alphas, but our questions are always about differences between them. That's how the comparisons we want to make. But let's pause on doing that and take a little bit of a break first. There's already been a lot of new material here, and please take a quick look back through the preceding slides, go for a small walk, have a cup of coffee, and when you come back, I'll be here. Welcome back. Let's pick up by finally analyzing the UC Berkeley admissions data. Just to remind you, this is what the data looked like. There's only 12 rows in the whole data table. Each row is a combination of a department and gender and its numbers of applications and how many were admitted and how many were rejected on each row. So this is a different data structure than we had in the simulation. And this is an opportunity actually to talk about the fact that count data can be structured in different ways, and we should just make sure that the statistical model meets the data in the right way, the way it's structured, so that we get the same inferences no matter how the data is structured in the table. Let me stretch out that explanation a bit. So what we've done so far is typically called a logistic regression. That is, there's a binary 0-1 outcome, and we assign its expectation, that is P sub I, a Logit link. And then we put on it some linear model. Here it's just an intercept, but still it's on the log odd scale, it's continuous value. In binomial regression, it's essentially the same kind of golem, same kind of statistical device, but now the outcomes are aggregated into cases as combinations of the explanatory variables. And so they are counts between 0 and some maximum number n. And that maximum number can vary. In this case, that number n is the number of applications to each department by a particular gender. And so it's data that goes in. And so we write the binomial regression. A sub I is distributed binomially. Binomial values are sums of Bernoullis. N sub I, comma, P sub I. And we're still modeling P sub I using the Logit link as before. These two forms are completely equivalent for inference. It should make no difference whether you do the 0-1 or do the aggregated counts. If you do it right, you get the same estimates, the same posterior distribution. This is what the data looks like in each case. So on the left, we have the sort of data that comes out of the synthetic simulation that we wrote. And this is a long table, long form, right? And all those zeros and ones, and each row is an individual application. But we can take the simulated data and aggregate it. I'm showing you the code to do that using base R's aggregate function. And you can aggregate the variable A, which is success or failure of an application, using the variables G and D. And then I run it a second time to get how many applications there are. And this gives us this new compact little data table with only 4 rows, where each row is a combination of a gender and a department. And this is what our data looks like for UC Berkeley, because that's the way it comes to us in this compact form with 12 rows, because there are 6 departments. Okay, so all we've got to do is take the statistical code we wrote before, change Bernoulli to binomial, and put the n variable, that is the number of applications, in the right spot in the binomial distribution. And that's what I'm showing you here. The binomial version of our model M2, the model with the matrix, that is where we simultaneously stratify by G and D, is shown at the bottom here. It's very similar. All the other code is the same. Okay, now we're going to analyze the real data now. So let's take these models converted to binomial regressions instead of logistic regressions. We build up we load the UCB admit data table, and then we make our data list, the sorts of lists I've been making all the time. The only thing to comment on here is I'm coding female applications as index 1 and applications from men as index 2. And you'll need to remember that when you think about the results. And then the departments in the data set come as letters, and I'm coercing those to integers because we want to use this as an index variable. Then the model to get the total effective gender, I'll call this MG, is the one that only stratifies by gender. And then there's the corresponding model that stratifies simultaneously by G and D to get the direct effects. So I'm just going to show the Précis output, but we're not going to stare at this. These tables are the things of nightmares. They're very hard to figure out. There's too many possible comparisons here to really understand what's going on. So for the moment, all I want to say is you want to take a glance at the diagnostic columns on the far right of each output. That is the NF, the effective sample size, as it were, of the chains, and the R hat, the convergence diagnostic. You can see in this case, these are good. We're getting good numbers of effective samples relative to the total length of the chain, which is 2,000 here would be the maximum. And then R hat 4. And you'll see that I think these chains on the right actually are functioning so well that they're highly uncorrelated, and we're getting even better than 2,000 effective samples in this case. And this is to take a look at the trace plot from the second model. This is the kind of habit you want to get into, is to make sure that these look like they're fuzzy caterpillar cells, and then the Trank plots. I find these much easier to read. You want to see them, that they're zigzagging in no particular chain is consistently above or below the others. Okay, let's do some contrasts. For models like this with categorical variables, our questions, our estimands usually require us to look at contrast effects, that is, differences between parameters in the posterior distribution. And since the parameters may have correlations in the posterior, we need to work with the whole posterior, not just the means, to think about these things. So let's think about the total effect. So in the code at the top, I've extracted the samples from the model MG, the whole posterior as samples. And then I'm using the inverse logit to convert the alpha for each gender on the probability scale. And there are 2 lines that do that, one for each gender, gender 1 and gender 2. And then I compute the difference in probability between the genders on average through both paths across all departments, right? Because this model does not stratify by department. And then that gives us the diff prob vector, and it's a vector because there's a whole distribution there. right? That difference is taken for each sample from the posterior distribution. And then I plot the density, and that's shown at the bottom. And what you see here is that all of the density is negative. It's below 0. This is on the probability scale. So the mean is around minus 0.14. So say on average, there's a 14% penalty for an application coming from a woman. Men are advantaged overall in the sample. This is one of the reasons the UC Berkeley leadership was concerned, is because they knew this was true. But this quantifies that. That's the total causal effect of gender through both paths in the sample. What about the direct effects? Now we're going to see something different here. The code is quite similar. Again, I extract the samples from the model, this time the model MGD. I use inverse logit. This time I do it on the whole matrix alpha. You'll see it there. It's inverse logit post 2 element A for the whole matrix. And so every element of that matrix, every sample in it, is converted to the probability scale. We now have a posterior distribution of probabilities in that matrix and not log odds values. And then for each department, I do sapply, which is just this way in R of doing a compact loop for each of the values 1 to 6, which are the indexes of the departments. We convert the relevant difference. We take the probability for gender 1, that is women, and we subtract from it the probability for gender 2, which is men. And then we can plot each of those. Now we have 6 posterior distributions, 6 contrasts, 1 for each department. So this is why we stratified by department, and we plot them all. And here I plot them in different colors, so you can see them at the bottom. And the vertical dashed line shows you 0. And again, this is on the probability scale. So most departments are very close to 0 and overlap one another a lot. We haven't done contrast between departments, but that's a calculation I'm confident you know how to do. I believe in you. And there's one department, the one in red, where there's about a 20% advantage for applications from women. There are a couple departments, like the purple and the blue ones, where women are slightly disadvantaged. There's about a 5% penalty, it seems, or let's just say we can't clearly interpret this as discrimination or anti-discrimination. All we know is that these are the rates at which these applications were accepted. But there's a lot of heterogeneity, and that's what you see. And that 14% penalty that's on the left is nowhere to be found. How does that average penalty arise, actually, in this sample? Where does that come from? Okay, so we just estimated the direct effect in each department of hypothetically intervening on the application's gender. But what's the actual expected effect of an intervention on an application's gender? So let's pause and step through this thought experiment, and there's something really interesting to teach here. The causal effect of intervening on an application's gender is going to depend upon the distribution of applications across departments. So even though we're talking about the direct effect of gender, it's going to depend upon the other variable. Let me step through this, and let's think about this carefully. The first thing to realize is that when we're talking about the direct effect of intervening on gender, we're not talking about changing the applicant's gender. We're talking about changing the perception of the applicant's gender on the application. So I've modified the DAG here to represent that, created a mediator on the path between gender and admission on the graph. Now, whether this intervention is plausible or not is something we'll talk about a little bit in the next lecture, but there's still something really interesting to learn here. So to calculate the causal effect of changing this mediator P, which is the perceived gender of the applicant, we need to average over or marginalize, the word is often used in statistics, over the departments, because different departments, as you just calculated, have quite different success rates for applications, both male and female. There are lots of ways to do this particular calculation. As usual in this course, I'm going to encourage you to do it as a simulation. I find this is easier to think about and easier to do calculations with and easier to modify. So here's the code. On the left, I know there's a lot of code there, but I'm going to talk you through it top to bottom, and I'm already showing you the result on the right as well. So at the very top of this code block, what I've done is I've just counted up how many applications there are total in the whole sample. And I'm going to use this just as an example for how many simulated applications we're going to do. We're going to simulate the same number of applications that were in the actual observed sample. And then what we need to do is count up number of applications per department. And you could do this with crosstabs, and here I've done it with a little loop, looping over the departments 1 to 6, and then just summing up all the rows in the data set that have that department ID. So now we have a count in apps per department of the number of applications per department. And that's what we're going to simulate, that many applications per department, as we observed in the original sample. You could change these numbers if you wanted to do the simulation for a different university or for some counterfactual where you change the number of applications per department. Then we have two code blocks which have the same structure. Use the link function to simulate observations from the posterior distribution of the probabilities of admission for each of the hypothetical applications in this. And so most of the action here is in the data list that I passed to the link function. This structures the simulations to be run. So D, the department IDs, we do all the departments 1 to 6, but each of them is present in the simulations. The number of times it was present in the sample, that's where the apps per department variable comes in. And then I set the N in the model to 1. That means it's just a logistic simulation. We do 1 simulation per. But remember, there are going to be 2,000 samples from the posterior here. So there's 2,000 samples for each of these rows. And then we set the gender to 1, to women in this example, because we're first considering the counterfactual that all the applications were perceived as being from women. And then the last code block down at the bottom, before we do the plotting, where we calculate PG2, same structure as PG1, but now as if all applications were perceived as being from men. And then at the very bottom, I just plot this contrast, the difference in all the paired samples between these two sets of simulations, and I show it on the right. And what you can see is that since there's that one department, it's department A in this sample, where women have about a 20% advantage in being admitted, and there are a lot, almost 1,000 applications observed for that department. Once we marginalize over departments, that is the peak, actually. The tallest mode in this is from that department. But notice that this straddles 0, and there are 2 modes on each side. And so this is one of those kinds of causal effects where the mean is not very representative of what's going on. It's clear there's heterogeneity that underlies this average effect. And so when we think about the consequences of the intervention, we have to take that heterogeneity into account. But this distribution gives you the expected posterior distribution of the consequences of changing the perception of an application from male to female. I've just augmented this slide to show you the specific direct effects of each department again at the bottom, but now I've tried to indicate their weight in the population with the thickness of the lines. And as you'll see, there are a couple of departments, red and blue, which have about 1,000 applications each, and those contribute the most to the distribution. But when you pile all these together in proportion to their presence in the sample, you get the distribution at the top. Okay, this topic is often called post-stratification. This is just an example of it. Whether we're doing description, prediction, or causal inference, often we need to post-stratify the specific parameter values or causal effects to some target population because we are any kind of realistic intervention is going to implicitly average over heterogeneity in the other variables. And so the causal effect of interest needs also to be averaged over the heterogeneity in those other variables. In this example, that heterogeneity is the departments and their specific acceptance rates for each gender. But in general, post-stratification means reweighting your estimates for any particular target population. It could be the same population the sample came from, but in that case, of course, samples and populations are different things. And the representation of the different groups, be they departments or cultural groups in your sample, may be different than what you know it is in the target population. And then post-stratification changes the presence of those categories in your simulation. In our case, for example, if you wanted to simulate the effect of changing the perception of the gender of an application for some different university, then you would change the distribution of applications across departments, and you could take the code from the previous slides and make that modification just by changing the number of apps per department. Okay, let's summarize. We've come a long way, and there's been a lot of information here. I appreciate that. Is there evidence of gender discrimination in this sample? The first thing to say is there's no overall overwhelming evidence for gender discrimination in this sample. So you can think about it, at least not direct gender discrimination in this sample. And the graph on the right is, in a sense, the most direct and orthodox answer to that question. To show it, there's some balance. Some departments appear to advantage applications for men and others from women. And overall, thinking about an average application distributed across all departments, it's balanced on both sides. Caveats, however. First, the distribution of applications across departments themselves can be a consequence of discrimination. Perhaps more women would like to apply to particular departments but do not because they anticipate discrimination or they feel that culturally it would be a hostile environment. Likewise, perhaps more men would like to apply to disciplines which are coded as feminine, but they feel culturally that they're not allowed to do so. Our data don't really speak to those questions, but that doesn't mean they're not relevant. That's a kind of structural discrimination question. The second thing, which we'll talk about a lot in the next lecture, is that confounds are extremely likely in these systems. In fact, it's impossible to rule them out, and their effects can be quite substantial. And that's what we'll talk about next time. Let me try to wrap it up and summarize for you. So this lecture has been an attempt to introduce you subtly to binomial generalized linear models through a particular motivated example that I hope is interesting. In binomial GLMs, as we sometimes abbreviate generalized linear models, the outcome variable is a count with a maximum. In this case, the maximum is known. We know how many applications there were to each department. But in general, that's not required to use a binomial GLM. Sometimes the maximum, the n in the model, is actually what we're trying to infer, as in cases of population size estimation. We used a Logit link, which is by far the most common choice, but it's not the only option. And there are other options which are scientifically justifiable. And finally, I didn't talk much about it, but I say much more about this in the book. The binomial distribution is the maximum entropy distribution for a count with a constant expectation. And I encourage you to take a look at the relevant chapter in the book about this, because it'll help you see how GLMs tie back to the early parts of the course where I said that Bayes is just counting all the ways that things can happen. So, for example, on page 310 of the book, I show you that even though for any particular expected value of a count variable, there are a large number of different distributions of the particular different possibilities that come out of it. So what I'm showing you here, for example, for any fixed expected value, I think it's 1.4 here, and this is blue and white marbles again. For 1.4 blue and white marbles as the expectation, there are many, many different distributions of the probabilities of each combination of white, white, blue, and blue, blue, because they could be correlated, right? Maybe they're not independent events. And the binomial distribution, however, is the distribution unique among all of these, which is flattest. And I'll say that again. The binomial distribution is the unique distribution among all of these distributions with the same expected value that is flattest, that is closest to being just a flat line straight across. For an expectation of 1.4, it can't be flat. It can't get any flatter than the binomial. And what that means is when we use a binomial distribution, it doesn't necessarily mean we're assuming the events are independent. It's just that in the absence of evidence that they are dependent upon one another, then the flattest and safest distribution we can choose is the binomial. Anyway, it's a long argument and it ties deeply to how Bayesian calculations are done. I encourage you to take a look at the long explanation in the book. Okay, that has been lecture 9. In the next lecture, we'll pick up exactly where we left off and think about how our inferences could be confounded and how we might deal with those. I'll see you there.